Hello everyone, my name is Mira Jürgens. I'm a PhD student at Ghent University, and in the current work, we analyze the faithfulness of evidential deep learning methods for uncertainty estimation by looking at the learned second order distribution. So, what is evidential deep learning? In general, it can be seen as a direct way of modeling uncertainty by learning a second order distribution, which then predicts both aleatoric and epistemic uncertainty in a disentangled way. This is done by training only one single neural network. For different problems, you choose your second order distribution to be the conjugate prior of your first order distribution. So, for example, for the classification case, you have the categorical distribution as your first order distribution, and then choose the Dirichlet distribution, which is the conjugate prior to the categorical distribution, as the distribution that you learn with your network. In previous works, some flaws of evidential deep learning have already been analyzed, and in our analysis, we look at the second order distribution directly and analyze whether it represents the epistemic uncertainty of the first order parameters in a faithful way. In order to do this, we first compare first and second order risk minimization. In first order risk minimization, we usually have a loss function, for example, negative log likelihood, and we do empirical risk minimization. Often, also a regularization term on the weights is added. In second order risk minimization, we have the same loss function, but then we apply an expectation over the first order parameters. And this expectation is either applied within the loss function, which we call inner loss minimization, or outside of the loss function, which we call outer loss minimization. We also have a regularization term, but this regularization term, however, serves a different purpose. It enforces the predictive distribution to look similar to a predefined distribution by minimizing the KL divergence. And this predefined distribution usually parameterizes the uniform distribution and the first order distributions. As an example, here you can see the experimental setup in our paper for the case of binary classification. So with our first order model, we learn the parameters of the Bernoulli distribution. And our second order model learns the parameters of the conjugate prior distribution, which in this case is the beta distribution. In our experiments, we use the same architecture and the same training procedure for both first and second order learners. So, how can we now directly evaluate the faithfulness of the resulting second order distribution? To this end, we develop the concept of a reference distribution, where we see the problem from a practical perspective. We say that the second order distribution should represent the uncertainty of the parameters learned by the first order models. To this end, we look at the underlying data generating distribution for a dataset of a fixed size n, and then define the reference distribution as the distribution of the first order risk minimizers, resulting from having training sets of size n. This is, of course, a theoretical concept, can, however, be empirically approximated by resampling from the underlying data generating distribution and calculating the empirical distribution function. As an example, here you can see the confidence levels of the reference distribution for the binary classification case for different sample sizes, where the true underlying parameter is shown as the green line here. In our theoretical results, we see that the learned second order distributions differ significantly from the reference distribution. For the unregularized case, we show that for inner loss minimization, we have the issue of non-identifiability, leading to a wide range of possible values for the estimated uncertainty. For the case of outer loss minimization, we converge to a Dirac delta distribution for all exponential family members, meaning that independent of our sample size, we always converge to a case of absolute certainty. For the regularized case, common ways in evidential deep learning to optimize the weight parameter lambda are mainly based on heuristics, thereby defining an uncertainty budget that cannot be exceeded, independent of the sample size n. Our empirical results confirm our theoretical results both visually and analytically. For more details, I refer you to our paper. As a conclusion, we can say that evidential deep learning does not result in distributions that are faithfully representing epistemic uncertainty. And the regularization parameter lambda just yields an uncertainty budget that cannot be exceeded for a given amount of training data points. Further analysis needs to be done on different regularizers and the case of more advanced second-order loss functions. For more experimental and theoretical results and proofs, check out our paper. Thank you for your attention.